Welcome to Lecture 7, Algorithms for Sequence Analysis. In today's lecture, we will study some filter-based approaches for approximate pattern matching. This lecture is based on these 3 papers and 1 PhD thesis, but essentially all information that we're going to be needing in the lecture is contained in the 3 papers, which you can find online. Okay, so what is filter-based approximate pattern search? In a pattern search problem, we have a pattern and a search database, and we aim to find all the subsequences in the search database that are similar to pattern using some distance metric, for example, Hamming distance or edit distance, with a distance not greater than a predefined threshold value. In the previous lectures, we have considered various approaches, for example, that would apply online searching after preprocessing of the query pattern, recursive traversal of ILSAP interval trees, and seed and extend heuristics. But all these methods, in one way or another, depend on the size of the search database. That is to say, the runtime as well as the space required to run these methods depends on the size of the search database. So a natural next step would be to try to reduce the size of the search database. And this is the idea of filter algorithms. In a filter algorithm, we are trying to reduce the search space to potentially promising regions, which would cover just a small fraction of it. So here, for example, in this schema, we have the search space denoted with S, and then we apply some filter criterion, which will identify a few regions in the search space which contain potential matches. It doesn't mean that they do contain matches, all of them, but all matches should be contained in these regions if this is a good filter. And then in the second step, we apply some conventional algorithm of the type that we considered before in the course to find the true matches. That is to say, a filter restricts this expensive verification phase to only promising regions of the target's search database. By the way, without losing the generality, we can consider the search database as a single very long sequence. So we have a pattern and we search for occurrences of this pattern in some very long sequence. There are generally 2 types of filters. A lossy filter may miss some true matches in the target search sequence. And a lossless filter contains all the true matches. And we are going to be looking for lossless filters in this lecture. A good filter always balances between sensitivity and speed, because the more sensitive a filter is, the longer it takes. In the extreme cases, a filter can take longer than the whole verification phase. So consider this figure here, which summarizes these types of filters. So this is our search database, and these are the true matches of our pattern. Lossy filter may miss some true matches, so it will contain false negatives. And a lossless filter, it might point to some regions which do not contain any true matches, but it doesn't miss any true matches. The central result on which we will rely in this lecture is called the Q-gram lemma. So first we introduce the definitions. A Q-gram is defined as any substring of length Q. So any sequence of Q characters from a given alphabet is called a Q-gram. Given some string S, more formally, we can define all Q-grams of this string. So any substring of length Q, S from I to position I plus Q minus 1, is a Q-gram. Here I must lie between 0 and length of the string S minus Q, including the boundaries of this interval. The problem that we are trying to solve is the approximate matching problem. Giving some reference text T and a query string S, the approximate matching problem with k differences and window length W consists in finding a pair of substring S from position I to position I plus W minus 1 and T, which is a substring of the reference text capital T, such that, as I said, S from I to I plus W minus 1 is a substring of S of length W, and T is a substring of capital T, and most importantly, the distance between T and S from I to I plus W minus 1 is not greater than K, where here we formulate this problem for the edit distance, but analogously it can be formulated for the Hamming distance. Now the Q-gram lemma states that if S from I to I plus W minus 1 is occurring in text T in position J with at most K differences, then there are at least this many common Q-grams between S from I to I plus W minus 1 and T from J minus W plus 1 to J. Now we will see how we can come up with this number of common Q-grams. That is the proof of the lemma. The first observation consists in that any difference between these two substrings destroys at most Q-grams, which we will call Y positions. The second observation is that in this substring of T, the last Q minus 1 positions contain no Q-grams because the substring ends there, so there are just not enough characters for a complete Q-gram. So we will denote them X positions. So if we subtract from the window length W the at most K times W destroyed Y positions and the Q minus 1 X positions, we arrive at this number of common Q-grams. For example, for Q equal 3, let's count the valid Q-grams between this target sequence and this query. So there is only one difference between the target and the query, and here are all possible positions. So we call the valid positions of Q-grams, we denote them with M, and here we also denote the Y and the X positions. So these are the positions that were destroyed by this difference, and these are positions which just contain no Q-grams. So here we see that we have 3 common Q-grams between these two strings. And if you calculate this value, which is the size of the window, which is 8 in this case, plus 1, minus 1 difference plus 1 times Q, you will get exactly 3. The first algorithm that we will consider in the lecture is called quasar. Quasar stands for Q-gram alignment based on suffix arrays. And the algorithm works in the following steps. First of all, we pre-compute the threshold alpha for a given window length W using the Q-gram lemma. Alpha will give us the number of common Q-grams that we expect to have between any two matches of the pattern and the search database. Then, for every window in the pattern, for each block of the search database, we will count the number of common Q-grams. Then we will retain only blocks that contain at least alpha common Q-grams. This gives us the candidate blocks that may contain the approximate matches of the search string. Note that the reverse is not true. If you have alpha common Q-grams, it doesn't guarantee you a match. And then we will move the window along the search string, the pattern string, and we will continue the search. To count the Q-grams matched in a window, we need an efficient data structure which is based on the suffix array. So for the text T, we construct the suffix array and then we create the Q-gram index. We create a table of size equal to the size of the alphabet to the power of Q that maps all Q-grams to their positions in the suffix array, which allows a constant time lookup in the text. So for Q equal to 2, we have this many different Q-grams, which is just the size of the alphabet 4 to the power of 2. which will be 16, and we create this lookup table which maps every q-gram to its position in the suffix array. We can easily encode positions of q-grams in this table, where we just map each character of the alphabet to a certain number between 0 and size of the alphabet -1, and then given a q-gram, we can use this formula to determine the position of the q-gram in the array. So the idea of QSAR algorithm is to keep a counter of common q-grams for a certain part of the search database T. It is not practical to keep such a counter for every possible window of length W, because for this you need a very large array of the size that is proportional to the size of the search text. Instead, we will just keep counter for a certain block of T. The size of these blocks is typically much larger than the size of the window. To avoid situation that is depicted here, where a true match is split between two blocks, we will keep two arrays of blocks of size B, which is larger than twice the window size. And the second array of blocks is shifted by half the length of the block compared to the first array. In this way, if a true match is split between two blocks in the second array, it will inevitably fall into one block in the second array. So for each such block, we can keep a counter of common q-grams, and if we find more than the threshold value of common q-grams, we retain this block for further closer inspection with some conventional approximate matching algorithm. The question is how we count the q-grams in each block for a certain window of the query sequence. Suppose we know the number of all q-grams for a certain position of the window in the block. Now we need to shift the window in the query and update this counter for the next window. How do we do this? So consider this example of q-grams of length 3 and this text, and we are shifting the window in the query sequence from position I to position j to positions I+1 to j+1. The only thing that we need to observe is how the number of the q-grams that are exiting the window changes and how the number of the q-grams that are entering the window changes. So these are the numbers of the q-grams that we have computed on the previous step for window in the query sequence from I to j. And now we are losing one q-gram, so we update the counter for this q-gram, and we are gaining one additional q-gram. It's not a new q-gram, it has been already seen in the text, so we increase this counter. If this were a new q-gram, then we would go to the place in the q-gram table which corresponds to this q-gram, and then you would have a 0 in this column, and you would just update to 1 just in the same way. Generally speaking, when we are shifting the window along the query sequence, we can update counters efficiently. In particular, we just need to watch for the counters for q-grams that are leaving the window and that are entering the window, so only for 2 q-grams. So for each shift update, we change the block counters as follows. We subtract the count of the leading q-gram which is leaving the window, unless for this block we already have more than the threshold value of these q-grams. Because if we have more than the threshold value, we can just stop here and submit this block as a candidate. And then we add a count to all blocks that contain this trailing q-gram. The success of filtering methods is measured by so-called filtration ratio. That is the proportion of filtered sequences, which means retained sequences, to the number of sequences in the whole database. So this is basically how much of the database we have retained to pass on to the conventional approximate matching algorithms. In the original Quasar paper, this was measured on the EST database. EST stands for Expression Sequence Tag, and this is what was used for sequence algorithms before sequencing became really cheap and accessible. Expression sequence tag is just a relatively short and relatively low quality piece of some genomic sequence. So for this algorithm, it is not important what sort of sequences are used. That was just a very large database available at that time. So what they did a all-to-all comparison of EST databases for two species, for mouse and for human. And here you can see in the first column the size of the database in mega base pairs, that is millions of base pairs, by today's standard that are not very large databases. And then for each sequence of this database, they used it as a query and searched in the rest of the database. These are the average length of the query sequences. And this is the key result. That's the filtration ratio, that is the proportion of the sequence that was retained for further alignment. That's the time that was used by the Quasar algorithm, and this is the time that was used by conventional BLAST. By the way, the conventional second step approximate matching algorithm in the original Quasar implementation was also BLAST. So all the gain of the speed that you see here is due to this filtering step. And these are some more results from the original Quasar paper. So what we see here is the different measures for different block sizes. Block size is the number of base pairs in each block that we have discussed. That is the part of the database that is passed on to the further approximate matching if we find enough common q-grams in it. So we are ranging the block size from 512 base pairs to 8,192 base pairs, and we are watching the filtration ratio, which is increasing with increasing block size, the alignment time and the filter time, and the total time that the algorithm takes. You see that the alignment time grows with the increasing block size, obviously because you have to run alignment on a longer part of the sequence, but the filtering time decreases because you have fewer blocks. And in the total time, there is some optimum between 1,024 base pairs and 2,048 base pairs. The disadvantages of the original Quasar implementations are the following. First of all, we consider here the q-gram lemma formulated for Hamming distance. But in the real world, we prefer to use added distances. So it would be advantageous to formulate q-gram lemma for added distances. This is in fact possible, and we will see how you can do this later in this lecture when we consider the Swift algorithm. And the second disadvantage is that using continuous q-grams does not provide you with optimal filtration. Now we will see how you can modify the q-grams to increase the filtration rate. In fact, you will decrease the filtration rate in that you will retain a smaller part of the database for further alignment step. Now, what are these gapped q-grams that you can use for this? Gapped q-grams stand for a string of characters where a hash character stands for a match, that is the position that we are watching that has to match to the sequence, and dot characters that denote gaps. These are positions that may not match. We don't watch for the character at this position. So this would be an example of 4-gram consisting of a match character, gap character, match character, gap character, match character. So in total, this q-gram encompasses 6 characters, which is called the span of a gapped q-gram. It turns out that gapped q-grams are more sensitive in detecting approximate matches. For example, for a window size 11 and k equal to 3 possible mismatches, standard 3 grams are not helpful in finding approximate matches, because the threshold for minimum number of common q-grams calculated using the q-gram lemma formula is equal to 0. So you cannot use 3 grams to look for approximate measures under these conditions. But if you use gapped 3 grams, you can do this. If you use a gapped 3 gram of this shape, you can just enumerate all possible distributions of 3 mismatches, and you always see at least one 3 gram in common. You are guaranteed to find at least one 3 gram of this shape. So you can use 3 grams to filter this in this setting if you are using gapped 3 grams. And the longer the q-gram that you are using for filtering, the more efficient your filter is. So gapped q-grams can improve the filter efficiency by actually orders of magnitudes. The problem is that threshold for a gapped q-gram depends on position of gaps. So for different gapped q-grams of different shapes, the thresholds are different, just as we have seen in the previous example. And the q-gram lemma cannot be directly applied to gapped q-grams. Let's try to find the lower bound for the number of common gapped q-grams. First, let's define a function t that depends on the q-gram with a span s of q and 2 non-negative integers corresponding to the window size and the number of the allowed mismatches, like this. Here R is the set of mismatches in a window of size W. The size of the set of mismatches is k because we have k allowed mismatches. And qi is just positioned gapped q-gram q at position I. So what we have here is effectively the minimal number of positions of q-gram that do not overlap with any mismatch, and the minimum is taken over all possible distributions of k mismatches in the window. Then we can formulate the q-gram lemma for any two strings p and s of length w with the Hamming distance k. The number of common q-grams of p and s is at least this function. And there exist two such strings p and s of length w with the Hamming distance k, for which the number of common q-grams is exactly this function t. Unfortunately, this doesn't give you a closed form for t, so it is not practical to use in any algorithm. One can try to formulate a lower bound. For example, one can prove that t is greater or equal of the maximum of 0 and w minus span of the q-gram minus size of the q-gram, that is the number of non-gapped characters, times k plus 1. If you apply this formula to the example that we have seen here, unfortunately for this q-gram, for example, this formula will give minus 1, so this maximum is going to be 0, which is also not practical. It is possible to formulate tighter bounds for special cases. For example, in the trivial case of contiguous q-gram, which is the standard q-gram from quasar, the bound can be proven to be what we have seen in the original quasar q-gram lemma. In the last part of the lecture, we will consider an extension of filtering algorithms for edit distances, called a Swift algorithm. When we were considering the Hamming distance before, it was enough to scan sequentially the search database with a window of the query sequence and count the number of qgrams in blocks of the search database. When we have the edit instance, we need to consider the whole dynamic programming matrix for it. And instead of blocks, we will consider parallelograms in the edit distance matrix. So the Swift algorithm proceeds as follows. First, given a window size and the number of the allowed differences, we compute the dimensions of the parallelograms. Then we split the edit distance matrix into some sort of blocks. Again, they will overlap just as the two arrays of blocks in Quasar. We will call them bins and we will count the number of common qgrams in them. Then we move with a window along the query sequence and we will update the counts for the bins. In this case, we will use a slightly different measure for the difference between the substrings denoted as epsilon. We define an epsilon match, or also a local alignment, as follows. Given a reference text A and a query string B, and the minimum length of the alignment n0 and maximum error rate epsilon, where epsilon is larger than 0, the task is to find all epsilon matches, that is, substrings alpha and beta from A and B respectively, such that the length of beta is greater or equal than the minimum length n0, and the edit distance between alpha and beta is less than the floor of epsilon times the length of beta. Additionally, we define a q-hit in the edit distance matrix as a pair of indices I and j such that the substring of A between I and I plus q minus 1 is equal to the substring of B between j and j plus q minus 1. Now we can formulate the qgram lemma on parallelograms. Let alpha and beta be substrings of A and B respectively, such that the length of beta is equal to n and the edit distance between alpha and beta is less or equal than e. Then there exists a n times e parallelogram such that first it contains at least capital T of q-hits, where capital T is defined as n plus 1 minus q times e plus 1. Second, its B projection is beta. A B projection is a substring of B between the first and the last column of the parallelogram. Its A projection is contained in alpha. An A projection is the substring of A between the last row of the first column and the first row of the last column of the parallelogram. And n times e parallelogram of the edit matrix consists of entries from n consecutive columns and e plus 1 consecutive diagonals. Now let's look at an example to make it clearer. Here we have our search database A and our query string B, and this is an n times e parallelogram where n is equal to 8 and e is equal to 2. So the edit distance between this substring of B and this substring of A is equal to 2. If we apply the formula from this slide, this one, we will see that this n times e parallelogram is guaranteed to contain at least 3 2-gram hits. In this case, every 2-gram hit is denoted with a bold line along the diagonal, where the corresponding letters are matching. Try to think of an example of B such that this n times e parallelogram will contain exactly 3 2-gram hits. In this case here, in the example, we have 4 2-gram hits here, here, and 2 here. Now, on the first step of the algorithm, we need to compute the dimensions of n times e parallelogram for our definition of the error rate epsilon. The next lemma shows you how you can compute this dimension, and it is the foundation of the Swift algorithm. Unfortunately, it is rather convoluted, so we're not going to prove it. Again, let alpha and beta be substrings of A and B respectively, and the length of beta is greater or equal than n0, the minimum length of the hit, and the edit distance between alpha and beta is less or equal than e. Then we define the function u as follows, and we choose two parameters q and tau such that q is less than ceiling of 1 divided by epsilon, and tau is defined like this, where n is defined like this. Then we can prove that there exists a w times e parallelogram that contains at least tau q hits, and w and e can be calculated using this formula. If length of beta here is less or equal than w, then the B projection of WE parallelogram contains beta, otherwise beta contains this projection. Now you see that these formula are a little bit uncomfortable and sort of messy. You can look up the proof of this lemma in the paper, but for our purposes it is not important how these equations have been derived. The important thing is you can mathematically strictly prove that you can compute the dimensions of such a parallelogram given n0 and the error rate epsilon. This example shows you the complex nature of relationships between all the parameters of the Swift algorithm. Here epsilon is set to 0.05, and for different values of q and of n0 you see different values of other parameters of the Swift algorithm, and you see that the relationship between them is rather complex. The next step of Swift, after we have computed the dimensions of the parallelograms, is the search step. So here in this schematic we have the subject, the database string here, and the query string here, which is a little inconvenient because compared to the example here that we had the query here and the subject here, so this is flipped over the diagonal. What we do, we split the subject into so-called bins of the size e plus some delta. So this is the size of the overlap between the individual bins in the matrix to ensure that none of the q-grams, none of the matches is going to be split between two bins. So what do we do next? We scan the query using the window of size W, and we start forming the n times e parallelograms by counting the number of common q-grams in them. So what we have here depicted as solid black lines are the common q-grams between subject and query. So we extend the parallelograms moving along the window, and we find the new ones. Here we see an example of Swift hits for certain parameters n0 equal to 20, epsilon equal to 0.1, and q equal to 6. When we apply the corresponding formulas, we get w equal to 20, tau equal to 3, and e equal to 2. So we are searching for 20 times 2 parallelograms that contain at least tau equal to 3, q-grams of length 6. And then we will extend these q-grams by some conventional alignment algorithm to a complete hit, to a complete epsilon match in this dynamic programming matrix. So in this subfigure we see an epsilon match that spans over two 20 times 2 parallelograms. In this figure, we see an extended parallelogram that contains 2 epsilon hits. In this part, you see a false positive filtering hit. Here, this parallelogram contains the required number of q-grams, but they cannot be extended to an epsilon hit. And finally, here we see just a parallelogram that contains one match. The results of SWIFT are assessed using the same filtration ratio as for quasar, and here the SWIFT filtration ratios are compared to quasar filtration ratios. Again, the database of expression sequence tags was used in an all-to-all comparison. So for some parameters, the error rate and the minimal length of the hit, you see that the filtration ratio is much smaller, which means that a smaller part of the database has been retained for alignment step, which is good. And the time is also smaller if you compare to quasar best filtration ratio, but it is larger than for quasar best time comparison. Similar filtering techniques are used also in modern tools that are used in the present-day practice. There is a number of read mappers that were made for analysis of next-generation sequencing reads against large genomes, which can employ the filters to reduce the required search space. Okay, to summarize today's lecture, we have introduced the concept of filter for string matching, and we have formulated q-gram lemma for lossless filter using the Hamming distance. And then we have considered quasar as an example of an algorithm that uses the q-gram filtering for fast local alignments. Then we have seen how one can extend the q-gram lemma to parallelograms of the edit distance matrix, and we have introduced SWIFT as an example of such an algorithm. Thank you, and see you next week.